What you can do is that you can let your computer running at night, playing my YouTube videos on repeat. So I can get some hundreds of views. You can be my bot factory. Anyway, guys, so let's go with group A, right? So go ahead, guys. Group A.
Okay, hello. Hello. And let me show my screen.
So let me just a second. Team A. Team A. Is this a new leader or the same leader? Oh, change of leader. Yeah, change of leader. Okay.
Yeah, we have change of leader.
Do you have a name for the team now that you are?
Not really. We don't really have a name, or you can.
Teammates. Okay. Okay. Very good. Go ahead.
Wait me a moment. Let me share my screen.
Hey, I'm sharing for you.
Sorry. Hey, you're showing it?
Yeah.
Okay. And okay. Can you? Okay. We are group. Okay, we're group A, and next page, please. I want to go to the overview. Next page. Okay, and this is our presentation overview. And for the exercise 1 and exercise 2, we have is in charge of the Ling Yuhen, which is doing the data processing and classic KNN implementation. And for me, I'm doing the exercise 3. And Barry, who do this work of art PowerPoint and doing the exercise 4, Barry. And for the exercise 5, we've got some problems because Zaid, which is our member, because of some personal issue, he tell us that he was not in Taiwan. He was not in Taiwan and was busy dealing with his problem yesterday. So exercise 5 still was not having any results yet, but I will try to finish it before the deadline and hand it on.
Excellent.
Okay, and for the exercise 6, which is for the visualization, which Halib will help us to do it. So with some picture or some graph in through the exercise 2 to exercise 4, Halib will help us to explaining what is the visualization was doing. Okay, next page, please. Lin Yuhan, thank you.
Okay, I'll tell you the part about data processing. So for data processing, we firstly converted the yes and no flags, such as the near object and hazardous flags, potential hazardous tables into 0 and 1 for KNN purposes. Next, we also drop some non-numeric and identifier columns such as name, ID, and timestamps, as they do not describe the object itself and does not contribute to the KNN. And also, I also drop the columns with zero variance as it does not contribute much to the VNN analysis tool. We scale the data to allow comparison between binary and continuous variables. And lastly, for classic KNN, we only use the working data set of 100,000 data collections to make the KNN effective. Okay, next slide.
Slow down a little bit for me, please. You are going very fast. Slow down a little bit. Go ahead.
Yes, of course. In our implementation, the class of the KNN is initialized with 2 parameters: K, which determines how much neighbors to consider, and the batch size, which helps to manage memory during prediction. In the prediction, during the prediction, we process the test data in batches. For each batch, we compute the squared L2 distance between every test sample and all training data using NumPy for clustering. It allows effective factorized computation without loops. After that, use the NT.arg partition to quickly find the indices of the k nearest neighbor for each test sample. After that, with majority voting, we determine the most common label among the neighbors. Okay, so as you can see from our slide, starting from the left, our classic KNN versus the K plot. So the accuracy improves as the K increase, and it peaks around K equals to 5, which gives a good balance between bias and variance. Beyond that, performance starts to level off slightly, showing that larger K values may move out important patterns. Local patterns. Okay, in the middle, the completion matrix for K equals to 5. The diagonal cells represent the correct classification, which I feel that it's quite strong for this classic KNN. However, there are still some misclassification, like in class of IEO may be confused for class of MBA, largely due to their features overlapping. This gives us insights as in which class are harder to distinguish and where we might need to process further wrong, where we might need to put in more effort to distinguish the classes. And on the the right hand side, the ROC curve shows how most classes have high AUC, shows that most classes have high AUC score. And take for example, AMO and APO both reach around close to a 1, which means they're classified that they have high.
Okay, just a second. In this figure here, I cannot see the third figure. Do you have a way to like blow it up a little bit? I cannot see the labels very clearly. Yeah? Hey, very good, very good. So this AUC, does it make sense to you? Do you want to explain what the AUC metric is? What is the false positive and true positive graph? But just because some people might not have seen it yet.
I can explain it. So here AUC is actually place under the plot, so place under the line. So the bigger AUC is, the bigger accuracy KNN has.
Correct.
So yeah, we can see that for example for APO, AMO, and CN, we have really like a big AUC. That means that our KNN model guesses successfully, and this black line here, you can see chance. It's a line that represents like absolutely random chance. So you can see that OMB has AUC equal to 0.5. It means that KNN guesses this class OMB with the same chance as just random. So
yeah, so these guys, so basically, yeah, for everybody. So basically, this is a way to represent the performance of a classifier in terms of zeros being classified as 1 and 1 being classified to zeros, right? So you have false alarm and missed. So the diagonal one is the performance if you have a completely random guess, and your algorithm should push the performance toward the left top corner. If you're on the left top corner, then you have best possible performance. And this AUC is a measure of the area under the curve. So AUC, area under the curve. And it's a measure of the sort of the overall performance of your classifier based on these two metrics, right? Okay, go ahead.
That's all. Can you go to the next?
Okay, next page is my part, and which is doing the feature-weighted optimization. And the way how I did it is I use so first of course, the data preparation. And because of our data set, the raw data set of the class, the column of the class was very imbalances. So the way how I did this is I just set up a threshold of how much of a percentage of which class has to be, which is for the raw data, 89% for the MBA, I guess, and 30% for the and 20% for the others, something like that, to make sure that KN have right evaluating, not just guessing the MBA. Because if we use a randomly pick 1,000 data sets, all of the result will be guessing MBA, and I think that was not reliable. So that's that's a reason why I did it. And the way I optimizing the feature weighted optimization, I use the grading search, because the problem will be like that, because the feature I take is 11 feature that which has the sigma, because I want to standardize it to make sure that each feature have a same weight when we evaluated the KNN. So, but the problem is if we use all the feature, which I mean the 11 feature with the sigma, and even that I only use the candidate of the 0.5, 1, and 2, there will still be 3 power 11 to need to search. So it will be a huge amount of data we need to do. So I'm using Grading to optimize it, but it's still very slow. I'm still trying to figure out how to make it faster. Okay. Yeah, and the method, how do I standardize it, was really easy. I'm not using the Z-score because I don't think that was reliable. The way how I did it, I just using the most simple statistic way to divide it, the sample divided by its own sigma to make it with the right to standardize it.
So you standardize to unitary variance. Got it.
And in the feature weighted optimization, my goal is not to find the most accuracy. My goal is to try to find the lowest cross entropy.
Yeah. Okay.
Yeah,
so you choose cross entropy as a okay. You choose cross entropy.
And the K I set, which for to fit the question, was 2, 4, and 6, and the result will be in the next page, please. Next page, which is the left corner right there. K equal to 2, and with the order by weight. Oh, why is the number feel like 0.0476? Because I want to make a, even that I say the candidate I use is 0.5, 1, and 2, but I'm make sure that the summation of weight will be 1. So I divide it again. Okay. And the result, you can see that the higher K, which will have a lower
cross entropy.
K4 and K6 is almost same cross entropy, but the accuracy, you can see like K6 have a higher accuracy. Okay. That's it. And for the next page, please. Excellent. 4. Sorry? What's 30?
So I work in this part, I work on weight distance canon. Basically, instead of treating all features equally, each features get a weight based on its importance. And I test different weight combination and compare how the accuracy changes. Overall, it helps the model adapt better in difference between features and improves the classification performance. Okay.
Okay.
For this part, this was the personal issue. He cannot attend today, so we only have just a page to describe how the exercise was doing. Okay, next page.
Yeah, so if he comes back, he can present next week. I'm always happy. I want to hear all of you guys describe what you do, right? So tell him that he can present next week if he wishes. Go ahead.
So this is my part about visualization. Here you can see graphs also for exercise 4. Well, first of all, ROC is like I would say extremely good for most of classes. Also you can see that still for some of them, like OMB, it's not so good. And on this graph, it's learning curve for k equal 5. You can see red line, it's training score. It means that on training data, this Kinin module remembers them perfectly. So it can guess anything on training data that it was trained on. And for cross-validation score, when it's taking some data it didn't see before, it's still very good. You can see that gap is not so big from
But is this on a balanced data set? Did you balance the data set here for these tests?
No, actually we didn't. We thought about it because
of course
on confusion metrics you can see like if I may, on confusion metrics, even like here you can see that data set is really unbalanced. We have like almost all MBA, and it's the same issue for all KNN models. So probably we'll do it in future. But yeah, here it's also making like better with more samples, but I don't think that it will be much better if we add more, as after like 2500 it's pretty same. Yep.
Very good. Okay, let's see the takeaways. Yeah.
This page is just a quick takeaway, the feature what we might need to do. Here, key tables just like that, data quality, drive performance, and something like that. And for the future work, for my part, which is the XS3 and I was thinking about to make it faster because it was really slow right now. Because the way how I did it, I use all of the possibility. So with like 3 power 11 times 1000 randomly data, it still need about 10 to 15 minutes to run it. So I was trying to develop a higher, faster way to do it. Okay.
Okay, very good. Okay, very good, very good. Yeah, you guys are the first group. Yeah. So some of so we discussed the AOC curve, which we didn't see in class. We discussed the data imbalance. Yeah, I think it's because you guys are the first group, so I think it's okay. I will not torture you too much. Okay. Any comments about how you guys worked? Were you able to synchronize effectively? Yeah, just tell me something. Did you meet in person? Just tell me something about that. Because the last time you met in person, right? Yeah. Any comment, guys? Okay. Otherwise, we move to group B.
Okay. Thank you, teacher.
Okay. Group B.
Hello?
Hello.
Hello, can you hear me?
I can hear you fine.
Okay, so I'm the leader of Group 2, Team Temp, and so some of the teammates in my group direct message me that he wants to drop out of the class, so he didn't finish his part, and the other guy I'm still waiting the other guy to finish his part too. And so now we don't have a finished PPT to presentation today. So I think we need to present next week. But I can still show you some of the result in my.
Show something. Yeah, as I said, be patient for this first. Still people dropping out. It's not good manner, right, to leave your if you had told us before, right, we will not have assigned it. But okay, I think students are not used to this type of consideration. So.
Can you
But
see
yeah,
my
show me something. Yeah, we can see it.
So here I did the classic KNN part, and here are some of the result of my part. So now I'll just show some. Let's see the localhost one. So here's some figure of my result. So first let's see the F1 score and error rate of the accuracy here. So you can see the accuracy getting and the error rate getting lower when the K gets larger, which means the model is more predicted data more correctly. But compared the F1 score, when K is larger, the score of F1 is dropping, which means the diversity of the prediction is getting lower. So in this case, I assume that when K is lower, the model is more, let me think, how do I talk to? The model can predict the actual class more accurate since the F1 score is lower in K is higher, which means the model is actually just guessing the biggest group to every single member in the dataset. And here is the confusion matrix of different K. Here's the K equals to 3. We can see the line here, which means the correct prediction, and some of the error prediction here. And we can also see the most group in the dataset is this MBA, just like the previous group find in their dataset. I don't know if we are using the same dataset, but basically might be very close since it's all from NASA. So yeah, the MBA set is the
Yeah. So
logic.
this is the crock of the challenge, right? That you have this dominating class, which is the MBA class, right? So you have to figure out how to deal with this issue, right? So that if you have an overrepresented class, how do you study the performance in this case, right? So this is the crux of the challenge. Go ahead.
Okay, so the k equals to 5 shows a little bit errors. Seems the minority group, the model won't predict it, so it only predict the largest group, and this is why its F1 score is lower than k equals to 3. And we can also find some thing in this heat map. And this is the heat map of k equals to 7. You can see more errors here because the model wants to guess the items to the one which is close to this zone to MBA. Their features kind of more close here, I think. And this is the scatter PCA plot, and the circle ones are the wrong ones, and we can see some groups separated, not very close, so it's the classic KNN model predict pretty well.
Just a second. So what is this? So you did PCA over the features. Then the colors are the different classes, correct? Well, what are the black circles here?
The circle is the wrong prediction. So in this one, I think it should be
let me pass this a second, right? Because here you see that basically PCA 1 and just a second, because basically looking at PCA 2, you can do most of the clustering, right? Because like the blue and the light blue, they're very and the green, they're very stripy, right? Then PCA 1. Just a second. Let's think about this. And then you have the misclassified. So which color is the most prominent class here? Is it the light blue? Do you remember?
I didn't write code to calculate the.
No, but here, do you remember which color is the MBA class?
I don't know. I forgot.
Because okay. And also the explained variance is kind of low, right? It's only 75%.
I think the more detailed explanation will present next Wednesday. I'll just figure this picture out.
Try to figure it out. Okay. Also here the features, you take the binary, continuous, discrete. How did you make everything work for PCA? Okay, you'll tell us next week.
Yeah.
I'm sure
so this is the PCA plot for k equals to 5. And here's on summary. Oh, it's broken.
Yeah, this is F1 micro position.
Yeah, just on accuracy. We have some accuracy here and precision macron. And
so the recall is very bad, right?
Yeah.
Yeah, anyway, so I understand you have had some difficulties. Just remember that, yeah, it's a challenge because the challenge in this case is this MBA class that dominates all the data types. And so all the measure that you want to do don't make any sense unless you decide how you're going to deal with the fact that there is a dominant class in the data set, okay? So just remember for next week, okay?
Is it okay to late submit?
In this case, right, you had people dropping out, you had people being late. What would be the purpose for me to punish you for it, right? What would be the point? Well, what if I don't let you submit late? What did you learn, right? I mean,
yeah,
that's the right question. So you should ask me, what is my objective, right? My objective is for you guys to learn something, right? Yeah. If I punish you for this, is there a message behind it? No. right? So of course, I'm sure that you did your best and you tried to communicate with everybody, and it was because the people were not responsive that you were late. So that's it. That's it. I'm not here to punish anybody. Okay.
Okay, thank you.
Very good. So group C. Here we have 4 missing people, and we have a new leader. So I'm sure the group C did a terrific job. Go ahead.
Okay, so just a minute, let me show you the slides. Okay, can you guys hear me and see the slides properly?
Yes.
Great.
You don't
Okay,
use
then
Canva. You use Canva, you use Google Slides. So you're like an old person like me, right? I understand. Do you know how many users Canva has? Do you know how many? Can you just guess how many users?
Just guess, maybe 1 million?
200. They
200
claim
million.
active users, 200 million active users.
Wow. And Google Slides do also have a
Let's check.
statistic about
That's
that.
a good point. That's a good point. Google Slides, active users. I think you don't have the number, right? Because they're not IPOing, right? So, yeah. Oh, they say 800 million people use Google Slides every month.
Oh, wow, that's a lot more than Canva.
Okay, but Google Slides doesn't
Okay.
have the integrated AI, right? People use Google Canva because of the integrated AI. So that's
Yeah.
Let's look for PowerPoint. Okay, that's it. We're doing this. PowerPoint is more than 15 users. I'll be shocked. PowerPoint. Who uses PowerPoint? Yeah, 650 million. You are joking. Who's using PowerPoint? Okay, I called you older, but if you're using PowerPoint, it's even older than me. Okay, let's go ahead.
Okay. Okay, so let me start the presentation now. Okay, can you guys see the screen? Okay.
Cowbay. Team Cowbay. Okay.
Yeah, that is a famous tourist spot in Hsinchu. Yeah. Okay, so we are team. We're group C, and we also created a name called Team Cowbay. And I'm the group leader, Liu Ye. And we also got Lin Xiang, Chen Weiting, Sun Ansheng, Yang Kaiming in our group. So today we are going to tell you guys what we did in this challenge. So this is our table of contents. So first we are going through how we process this task and how we deal with the data set. And then other group members will tell you about what they did in the classic KN and weighted KN parts, and then make a series of comparison about how we done. And in the end, we will make a brief conclusion about the task. So let's get into the first part. Okay, so in this task, we are dealing with a data set from NASA, and we split it in a ratio of 80-20. That is the training part and the testing part. And the test size is over 10,000. It is a little bit large, so we do spend a lot of time when running the program, and it also hold a lot of memory when we are running a program. Yep. And in the processing of the task, we first do some centralization to the data, and then we dimensionality reduction to it. That means we make it into a 2D data so that we can make a better manipulation about it. And in the KN interface, we do the classic part and the weighted part. And for the weighted part, we use this formula to calculate weight.
So what is
And
DI? What is DI here? What is DI?
now that is the distance to each group. And we also use this formula to generate the weight and also add a little parameter generated by AI. Yeah.
Question. On the dimensionality reduction, you have some continuous and some categorical features, right? How did you deal with that?
Excuse me, can you say the
So you
problem
have
again, please?
features and you have some categorical features, right? How did
Yeah.
you deal with it when you do PCA?
Oh, that part, I didn't really, I don't know too much about that. Maybe my group member will tell you more, but, or
Okay.
maybe not because we are using AI to do that part. Yeah. Okay, so in the end, as a result, we generated the graph is by these parameters and indicators so that it can better visualize the result. And next, we are going to the classic KM part.
Okay, and this is my part, and my name is Cheng Wei Ting, and you can call me Will. And let me start with a quick refresher on classic K nearest neighbor. And in the graphic, the green point is the sample we want to classify. And if we pick K equals to 5, and then we find its 5 closest neighbor and let them vote for the class. The choice of K's matter because too small, and if it's too small and we're going to be noisy, and if it's too large, then the decision boundary gets overly smooth and can drown out of minority classes. Okay, next page, please.
Okay.
And this slide shows our baseline, K equals to 5, and with PCA 32 features. And KN inference cost is the big O notation, and the number of tests times the number of the train times the dimension. And the data set, the N is very large. So a naive O pair descent in high dimension can take days. When I train this data or train this KNN, I spend like 12 hours and it only complete 30%. So we cut that to 30 minutes with 2 moves. First of all is PCA 32. We string the dimension to 32 and we vectorize math in flow 32. That is, we compute the distance by batches using fast metric operation. Yeah.
Very good, very good. Okay, yeah, because this was part of the things that I want you to observe with the challenge, right?
Yeah.
So of course you have a very large data set, right? So when you want to do KNN, you have to wait throughout all the data set to find the closest one, and you simplify this by using PCA.
Yeah.
That's my question to you, right? How do you compute PCA? How do you compute PCA, right? Because some of the features are categorical, some of the features are quantitative, right? So how did you do the conversion to a vector over which you can apply PCA? Do you remember?
Yeah, I do remember because the way I do PCA just call those functions and Python did it for me. I know it do some like PCA is called principal component analysis, I assume. So I do know it attracts some principal component, but the detailed way to compute it, I don't really know because I just call some function to do it.
I understand. Yeah. So this is the issue, right? So
yeah,
I
just treat it as a black box.
Yeah. But so you did linear algebra, so you know what is SVD, correct? You know singular value decomposition.
Yeah, correct?
I do. This is just SVD. PCA is just SVD.
Okay.
We're going to do it later on, but PCA is just SVD, right? So it's just a
All right.
projection. My point, I mean, I think you learned the point, right? My point here is that, so the first group described how they did the quantization of the features in order to make everything categorical, and then they did the dimensionality reduction over there. But here, I think, what do I want to say? I think this is something that we discuss in class, right? So how to harmonize continuous and discrete features. What is the one-hot encoding and so on and so forth. This is one of the big, this is one of the big things that I wanted you to notice. So, yeah, maybe try to go back and try to understand what is the principal way of doing this. Okay, go ahead.
Okay. And so our baseline overall accuracy is about 0.877, but the F1 score is about 0.7. So you can see the strong score for dominant classes, but for some minority classes have support as low as maybe 1 to 15 samples. So nearly zero F1 score.
Correct.
Yeah. Next page, please.
Okay.
Okay, and on the left is a elbow or so-called knee plot, and x-axis is K, and y-axis is error rate.
Let me ask you a question.
Yeah.
Let me ask you a question here. So here, did you take all the samples? Did you do some data set balancing, or you just tell me how you did this?
I think it's also past the PCA, so it calculates faster. And yeah, I do some balancing.
Okay. Well, how do you do the balancing? Can you tell me?
Using those weight, I remember I did. Like next prisoner, maybe talk about it much more.
Okay.
Yeah.
Okay. Very good. Very good. Okay. Go ahead.
So the y-axis is error rate. So the curve drop at first, then flatten or rises past the knee, telling us not to choose a much larger K, because it got higher error rate. And you can see there's an square root of n. The square root of n is about experience, because I Googled it, and some people tell me about if you use square root of n, you can treat it as K. But when I do the elbow or knee plot, it says the K is about 9. Yeah. And the right one, on the right, we can see an overlay accuracy and the F1 score versus K. And accuracy peaks around K equals to 8 to 12 and then flattens. But the F1 score decline as K grows, because when we widening the voting neighborhood favors the majority classes even more.
Correct. Yeah. So are you happy with this or not? Are you happy with this or not?
I think it is good because the accuracy is pretty high. I think it's okay.
But your model is just predicting the majority class for most of the times, right?
Yeah.
So does it make sense to have a predictor if the predictor is just going to say that it's the MBA class?
I think it's pretty good.
Okay.
Yeah. Okay. Next slide, please. Okay. And the left one is a confusion matrix. So the confusion matrix is the brighter along the diagonal means the better. And you'll notice strong diagonal for those big classes. It is very strong for those big classes, but very faint for those minority in the diagonal, meaning they're often misclassified. And the right one is one versus rest ROC curve. And most classic hugs, the top left corner, means they got high AUC, while a few minority classes have flatter curve, means they got a lower AUC. And the red dashed curve is a macro average AUC. Okay, next slide.
Question, what does ROC stands for?
What? Sorry?
What does ROC stand for?
ROC is I think is receiver operating characteristic curve.
Excellent, excellent.
Is
So
it?
because this terminology comes from the days of the radio, right? So
Yeah,
when
yeah.
people receive digital messages and or more, you know, it was a way to describe the performance of the receiver. Yeah,
Yeah,
very
yeah.
good.
Okay. Next slide, please. And the left one is our decision boundary. It looks
Nice.
kind of funny, and I gonna discuss it later. And that's our decision boundary in PCA2D space. Because KN has no parametric hyperplane. The boundary is entirely data driven. And the top right is a learning curve. It's about accuracy. It means more training data steadily helps. And the bottom right is learning curve. It's about cross entropy. And it decreases as we add training, means the model probability estimates are getting more confident. Yeah, and you can see there's a point in the lower left corner of that decision boundary. And that point, about that single point, I think that is the best interpret as an extreme outlier in PCA2D projection. And if we fit PCA on the training set and project on the test set, if a test sample is very unusual or belongs to a very rare class, its first two principal component can land far from the main cloud, given next slide, please. Given the asteroid data set, we're looking for some classes. And those classes are only support for 1 to 15 sample, right? And I see a vivid and realistic example is called Democloid. Democloid like asteroid. And I think of an object of Democloid is Daurita. Okay, next slide. And Daurita is a very high how to call that word? Eccentricity. Have a very high eccentricity, and it retrograde and got high inclination and got large semi-major axis and long period and very dark surface and only a few kilometers wide. So it's pretty weird. It's a pretty weird one. So after standardization, such an object is extreme for PCA. So PCA first two component pushes to remote corner. So that's a dot you see. Yeah.
So do you have a background in astronomy, or tell us about you?
No, I got background for double E, but I have some I like those astronomy. Yeah.
Very good, very good. So I'll return you. Can you go back to the boundary? Yeah, that's a nice plot. Yeah, so we, of course, the class is an undergraduate class. We don't have time to explore everything, but you can think about this, right? So in order to draw this boundary, right? Let's say that you only need a fraction of, let's say, 5% of the data set, right? So that in a sense, right, you could try to have the same performance just using a very small subset of the data set and throwing away all the other data set. So in some numerical structure, so in some implementation of KNN, what you do actually is that you only store those elements in the data set that help you draw the boundary. Because here we're not doing regression, here we're doing classification. And so you could drastically decrease the data set that you use for KNN if you figure out which sample you should keep in order to have the same boundary. Because of course, many points in the dataset don't contribute to the boundary, right? So they are not useful. Yeah. And also, yeah. So also go ahead with the slide. Yeah. So this is. Go ahead with the slide, please. So this is the discussion as of why we have to decide, right, what is a good model, right? Because of course we have a majority class which said the asteroids are not it's not dangerous, right? It's but of course we are not happy with a model that just says all asteroids are innocuous to us, right? Because you want a model that prevents what is called the black swan, right? And you want a model that also takes into account of some very rare events that are very catastrophic for us as a human race. So this is part of the challenge, right? That understanding that what is a good prediction is a much bigger question than just looking at the loss, right? Anyway, go ahead. I think you understand what I'm saying. Go ahead.
Okay, and that's end of my part.
Okay, the end of your part. Very good, very good. Go ahead.
Okay, now I'm going to talk about some classic KNN versus weighted KNN index. And this is the PCA 2D scatter. And this slide projects all samples into 2D PCA to visualize class distribution. And I have used two visualization tweaks. The first one is downsampling, is to keep the figure readable, because there are too many dots. And the second one is robust ACES limits, which is 1 to 9 sign percentile, plus a lower right overview inset to show the global spread. As you can see from the down right, the overview is really big, and there are some parts that really have many dots, but we can't see it if we have to. So we have to shrink it to not shrink it, to make it bigger to see what's like it. Yep. And so the way the matrix changes the relationship in feature spaces. You can see in the classic matrix, all samples are measured using the same distance function. However, in the weighted matrix, especially when class weights are introduced, the model rescales distance according to class frequency or sample importance. So you can see in the weighted matrix, it feels a bit wider than the classic matrix.
Good point. Good point.
So I think that it's because for minority classes, distance are compressed, and for majority classes, distance are expanded. So when PCA computes the coverage matrix based on these reweighted distances, their overall variance directions shift, making each class distribution appear wider in the projection.
But your weighting strategy is fixed, right? So you just look at the radius of the cluster, right? So you didn't learn. Okay, you fixed your weights ahead of time. So why did you end up with this idea of using this formula for the weights?
You mean the formula?
Yeah. So if you go back,
how to. Yep.
Yeah. Go ahead. Go ahead.
I Google it, and it tells me to do like D plus E 1 1 1. Yeah.
I think that you understand the limit of Googling, right? I mean, you understand that if you had chosen, like you had many strategies to play with and to test with, right? But the fact that you Googled it prevented you, it made you land on one solution, you didn't explore the others, right? I think throughout the presentation today, you're going to see some of the strategy of doing this, and some would make more sense. Yeah.
Okay, next page. So these two plots show the learning curves for both accuracy and cross-entropy loss. And you can see it's, as we have seen, that the weighted curves are better. But I want to say something that I found kind of weird. You can see the learning curves cross-entropy from 0.5 to 0.7. It actually increases, classic one. And for me, I think the possible reasons for this increase is because of the decision boundary readjustments. But when the training fraction increases from 0.5 to 0.7, the model encounters maybe more diverse samples. especially those near class boundaries. So this changes the neighborhood structure of KNN, so causing the decision boundary to shift suddenly. So as a result, some samples are still classified correctly, but the model's average confidence for these predictions decrease. And another thing I think maybe is because of the class imbalance effect. So during this stage of classic, matrix is affected by the proportion change of minority class samples. So since it does not use class-weighted KNN, tends to favor majority classes. So when new samples alter the dominant class ratio, the model rebiased for certain classes, so making previous confident predictions more uncertain. So this appears as a rise in cross entropy without a significant drop in accuracy. Yeah, next slide.
Okay, so how is our comprehensive comparison? And next slide, please. So these panels are the confusion metrics, and we can see that on the left top is a classic one, and the bottom of the left is weighted, and it sharpen the diagonal of the graph, and it's not really clear, but like it's sharpen it, and the right side is a regularized one we make, and we use the gamma equals 0.5 to make it better.
So what is the gamma? Yeah, what is the beta and the gamma?
I think it's the like the voting, like I'm not sure how the code works, but it's like the possibility. I'm not really sure how it works, but like it's regularized it by different weighted we give it.
Okay, yeah, try to figure out so you can tell us, like in the final presentation, what is the value here, right? Because you don't talk about this parameter anywhere, so I don't know what are the beta and the gamma. Yeah. Go ahead.
Okay, next slide, please. And this is the PCA's visualization, and the classic, which is the top left, has more overlap near the origin, and the weighted, which is the bottom left, has sharpened the structure, fewer straight points, and the top right adjusts class proportions and both together. The bottom right one just keep the cleaner geometry while stabilizing predictions. And next slide, please. Next slide, yeah. Okay, so this is the one of PCA 2D, and the classic KN gives a fuzzy vertical frontier near the origin, and adding prior correction alone gives the same geometry, but rebalance region size, and the weighted bottom left sharpens and shifts the frontier. And so together, the bottom right, we get a crisp boundary and better calibrate class coverage.
Stay there a second. Stay there a second. Yeah, that's beautiful. Yeah, that's nice. Nice. So classic regularized, k is equal to n, k is equal to 11. Okay, the regularization really helps bringing out the class number 8, right? Because class number 8 was not present with the regularization. That's nice. Go ahead. Go ahead.
Okay, next slide, please. And this one is the learning curve, and the left one is like the left is accuracy, right is cross entropy, and the top one, k equals 9, and bottom k equals 7. As training data goes, both models improve. The orange red orange line is consistently above or equal to blue and has lower CE, and like especially small data. And the weighting raises the overall ceiling, while regularization stabilize and better calibrates the probabilities. Next slide, please. Next slide. And this is like the conclusion. So when we got k equals 7, this is we have the best macro F1, the highest macro F1 data. And when we if we want to get the best accurate goal of total, we will choose k equals 9 or 11, but both are accurate. The accuracies are both 0.9192. But when we choose k equals 11, the CE, which is the calibrate error, is lower. So 11 is better.
Okay.
Next slide, please.
Okay, so so after doing all this research, I started to think what KN can really do in our real life. So here's what I found. So first, KN can be used to predict the user behavior in, for example, Netflix or Amazon, that when the platform want to recommend you something, they can, based on your behavior, to group the similar users' behavior with you, and then furthermore, the platform can recommend the similar stuff or similar movies to you that you may be interested in. And there's another interesting usage we found, is to prevent the illegal use of the credit card. Because when you are using a credit card, it will, if it is a abnormal use or a illegal use, it may generate a result that is very apart from the original data sets, just like that weird Android in our previous slide. So that by this way, we can easily find that this transaction may be illegal or weird, so that we can do our best to prevent the criminal.
Okay, very good. Very good.
So here's the end of our presentation. Thank you very much.
Very good. Very good. Yeah, as I said, yeah, some things that you guys could have improved. The weighting, I think you could have explored some more strategies. Also, yeah, I would have liked to see a little bit more discussion on like what is a good model when the class imbalance is so large, right? I think you had a good example with the asteroid that was out of class, was an outlier. But, yeah, otherwise, good job. Good job. Very good. Okay, so let's take a quick break. If you guys have any question, I'll see you back in 4 minutes. Okay, I'll see you back at 2:30. Okay, go
wait.
walk around, drink some water. We talk soon.
Wait, we're Professor.
Tell me.
I'm Group D for challenge 0, and
Okay.
and when we see the feedback, we saw there is a weird comment that you wrote. We talk about naked woman on our presentation. I'm just curious about why we had that kind of comment.
Wait a second. Let me remind you. It was a joke, right? Wait a second. Wait.
I'm not sure. I'm just.
I mean, wait a second. Wait a second. Let me. You said Group D, right?
Yeah, challenger team.
Wait a second. I forgot, what was the joke, guys? Anybody remembers what was the joke? What was the joke that you guys made? Come on, guys. Somebody remembers, right? What was the joke? The joke was... Oh, gosh, I have to go back to the video. It was a joke, right? I don't remember. But it was a joke, right? It was a joke.
Because I'm not.
You remember what was the joke?
We only play the video for a presentation, so I'm not sure what's happening for our presentation. So
because it was about movies, right? And one of the things was nudity, right? And then we were discussing something about the clustering of the nude. It was something like that. Yeah. But there are some weird comments, right? In the on purpose, I put some weird notes for myself, right? So
okay.
I remember stuff, right? I'm not gonna report you to the police, but yeah, it was. Yeah. If somebody remembers the joke, please let me know, because it was something funny that you guys said. Yeah. It was nothing serious, right? So sometimes I also complain that there are some people that speak too fast, right? Of course, I have to make it entertaining for myself, right? We are here 2 hours and a half, 3 hours listening to you guys. You know, I have to try to wake up my brain sometimes. Okay, no problem. Let me go walk around and be okay. We talk soon. Ciao.
Okay.
We were long. Okay, group D. Let's let me check the comment here. Lab and Python. Let's see, naked. These are a good thing. I see. September 24th. I'm checking the comment. Okay. I remember. I know. I found the. Okay, let me just share so that you see how to use Otter AI, right? So there was this comment about a certain comment I left, right? So I went to check there, right? And it was your presentation, right? So we're talking about film noir, right? And we were talking about we're talking about different film noirs, right? And what the students said, I saw it in the cinema and she's naked, right? So that's where that's where discussion was. Yeah. Go watch a movie now because there is a woman. I see. Which movie were we talking about, guys? Yeah, it was a film noir movie, right? And I told you to go watch it because it was great. Yeah. I don't. Anybody remembers what's the movie? Yeah. Yeah. Anyway, so that's now I remember the discussion. Yeah, and this was the discussion. Very good. Okay, very good, guys. Now we figured out where the comment came from. Okay, group D. Thank you, guys. Go ahead.
So I have to show my screen.
Well, let me just check a second my notes about group D.
Can everybody see my screen now?
Yeah. Give me a second. So group D, group D. So you have 4 people, 1 missing, same leader. That's where there was a confusion about the old leader and the new leader. Okay, very good. You guys figured out the power struggle in the group, right?
And we have all teammates now.
Okay, very good. Group D, go ahead.
Okay. Hello, everyone. Wait. Hello, everyone. We're Team Eureka, and today we present our work for Challenge 1, focusing on the weight K nearest neighbor algorithm. And our goal is to improve the classic KNN model by using the weighted and the regularization KNN. And here is our team assignment. I took the charge for the reporting and the presentation. Chen Yu work on the weighted KNN, and Minxi will handle the regularization KNN. Xin focus on visualization, and Rickard implement the classic KNN. And our presentation is organized into 5 parts: introduction, classic KNN, development, and weighted KNN development, regularization KNN for balance classification, and result and visualization. And now for the introduction. Our data set consists about 287,000 attributes across 30 orbit classes.
Let me stop you there. I think you are sharing the PowerPoint program page and not the presentation. Try to switch to the slide. Okay, now we can see you move. Yeah. Now we try to share the presentation, the full screen presentation.
Is that okay now?
Now we can see your. So you share the. Now we can see also your notes. So try to share the.
Oh, I know.
I think you know what to do.
Yeah. I have 2 screens now. I have them.
Yes, he has 2 screens.
Yeah.
Okay, very good. Move. Okay. Yeah, also the animation. Perfect. Go ahead.
Okay. So for our Osprey data set, we have 287,000 asteroids and across 30 orbit classes. And the 3D features we used clearly shows the extreme imbalance, where we separate into 3 classes. The main belt asteroid dominates over 80% of all samples, while the near-Earth and outer Neptunian classes are rare. This imbalance motivates our work on weighted and regularization KN approach. And now we're moving on the classic KN algorithm development. I think my teammate should present this part. Okay, it's okay. So we first evaluate the classic KN with varying Ks and accurately slightly increase at K equals to 5, but the precision and F1 drop at a bit. So the MBA forms a dense central region for our 3D diagram, and near-Earth classes are overlapped. And outer systems sparse because there are too few samples for the training, I think.
No, stay here a second. Stay here a second. Can you stay? Can you go back one? So here you have the eccentricity. No. Stay there.
Yeah,
Stay there. So semi-major axis, eccentricity. What's on the y-axis of this 3D plot?
Wait.
Yeah, what's on the y-axis?
Y-axis is.
Is that a distribution? No. What is it? What's on the y-axis? No, it's not the. What is it?
Maybe I should ask our teammates because he is online. Let me check. She said his mic doesn't work.
So try to connect. Try to connect with your phone, and you can use the use the phone maybe. Okay, smart, huh? Smart guy.
Yeah, I still use PPTs. Yes.
I mean, you can do very good animations, right? So I understand why you don't want to move to other platforms. Yeah. So then accuracy increases slightly at k equals to 5, but precision from one score decreases slightly. This indicates that the model is more stable with larger k, but at the expense of undiscriminability. The optimal overall balance remains between k equal to 5. Yeah, Ricard, tell us.
I'm on my phone now. Sorry for the problems.
No problem.
But let's start here. We made a KNN classifier model in the asteroid dataset to classify asteroids based on their orbital properties. We used 70% for training and 30% for testing. The predictors we used were semi-major axis, eccentrics, and inclination. These predictors will predict the class, like if it's an Apollo, an Amor, etc., etc. We tested the KNN classifier model on accuracy, precision, recall, and F1. As you can see in the table on the right side, for KS5 it achieves the highest scores on average. So we recommend to use KS5, as this will lead to the best results, because you won't generalize too much, but you don't have just one neighbor. So that's the best of all. Asteroid, it's a really good KNN model because it has all values above 0.93, which means it's very good. Means it's a very good model. And furthermore, on the left side, you can see a 3D model where they predict based on the predictors which output it will have. That's it. You can move on.
The categorical variables you drop. You just keep 3 variables, yeah?
Three variables are the predictors.
Okay, very good. Go ahead.
You can yes. You can move on.
Okay. So next part.
Yeah, I'll be presenting on this part. So it's about weighted KNN. So usually the classic KNN, not all neighbors are equally reliable. So weighted KNN fixes this by assigning larger weights to nearer neighbors and smaller weights to distant ones. And next slide. Yeah, so here we are comparing per class recall between k equals 1 and k equals 2. And you can see that the long tail or minor classes like AST and ATE, they have very low recall below 0.2 regardless of k. And major classes such as APO or AMO dominate the performance. And this highlights a key challenge with KNN as it favors majority classes, which motivates the need for regularization. So on to the next slide. No, the previous slide. Yeah, this one. So this is a model performances as a function of k. So we look at how performance changes as we increase k, and accuracy peaks at k equals 2, reaching around 0.947, while macro f1 is slightly higher at k equals 1. And beyond k equals 3, both metrics start to decline, suggesting too many neighbors dilute the local decision boundary. So overall, k equals 2 offers the best trade-off between accuracy and generalization. Next. Here are the results of feature weight optimization, and all 3 features groups converge to equal weights about 0.333 each. And this uniform distribution indicates that after scaling, all features contribute equally to distance computation. And in other words, the model is well balanced and not overly dependent on any single feature group.
But
Next.
let me comment on it. That's because you just took 3 features, right? If you had taken multiple features, the story would have been probably different, right?
Okay,
and also, if some of the quantitative features, you would have decided how to manipulate them so that you have some dense representation of these features.
Okay.
Right, it's good. So how did you optimize here? How did you optimize the features? Can you tell me? Did you run some games? So here you must have optimized the features before this. So you were optimizing F1 score or?
Accuracy and F1. Yeah, accuracy.
So you were not accounting for the data set imbalance, right?
Yeah.
I think that's another issue probably, right? Because so you're saying that if you consider the whole data set, that's what I wonder, right? Because probably the prediction collapses to the most frequent classes, right?
Yeah.
Optimize the accuracy. Because the fact that you get them exactly equal is going to be fishy for me. Because it means because probably the initialization, you need to initialize them to be equal also initialization, correct?
Yeah.
So that's what I'm thinking. That probably maybe it's possible that the optimization didn't do anything, and so you just stayed at your initialization, correct?
Okay. Yeah.
And so that means that the model is always predicting the MBA class, right? And so there's nothing to optimize because whatever you change it, you just the optimization will always lead to this degenerate case where you always go for the most likely class.
Okay.
That's my concern. Huh?
Yeah.
Okay, go ahead.
I'll look deeper into it. Thank you. Yeah, so the next slide. Yeah, so these are the confusion matrices for k equals 1, k equals 2. And the dark diagonal blocks just show correct predictions, especially for strong for classes of MB, IMB, and OMB. And however, classes like AMO, ATE, IEO show more off-diagonal confusion, meaning the model mixes them up. And moving from k equals 1 to k equals 2 slightly smooths out these errors, giving more stable predictions. Next. So next we have the ROC and AUC overall discrimination ability. So here we visualize overall discrimination using ROC curve at k equals 2. And the area under curve is 0.982, which indicates very high separability between classes. However, note that it's a micro average ROC, which means it hides the imbalance problem. So while overall performances looks great, minority classes still struggle. So finally, the learning curve for k equals 2 shows that accuracy quickly saturates and the model is already data sufficient, and adding more training data won't improve much. Macro F1, however, fluctuates due to class imbalance. So the next step should be balancing or reweighing the classes to improve minority class performances.
Very good, very good. I also like the ROC joke. Okay, ROC. Very good joke. Go ahead.
Okay, so now I'll be presenting our regularized KNN. So next slide, please. So the way we choose the weight for our regularized KNN is as follows. It's inversely proportional to the distance and the frequency of the class. So as you can see, it's a relatively simple strategy of deciding the weight. So I think it can be seen as some kind of degenerate version of the previous one, the weighted KNN, since the decision is actually simpler. So, okay, next slide.
Well, this is very aggressive though, right? Because if you divide by the frequencies, then these MBA samples will count for nothing, right? I'm curious to see how it performs. Let's see how it performs. Very curious. Go ahead.
Yeah, we have no time to try other things.
No.
Okay. I'm sorry. Okay. So here you can see the most minor classes are the recall is still very low. So this shows that even with regularization, it struggled to correctly identify rare samples. But for mid-frequency classes, the recall is relatively stable, around 0.5 across k equals 1 and k equals 2. So it's about the same as the weighted KNN 1. So next slide. Yeah, so here is the main part where
Can you tell me? Can you go back to the formula? How did you come up with this formula? Did you look it up somewhere? Did you dream it up? Tell me. Was it on a carton of milk? How did you choose?
You say the
formula for
last time.
Yeah, the W.
上页. Yeah.
How did you come up with this formula?
Well, I just choose the ones that satisfy the demand of the PDF, but I didn't really. I've seen some other implementations, but I'm out of time, so I just use this.
I guess the other classes, you like the other classes more, right? I guess that's it, right?
Oh no, it's our grad school application week, so we are very, very busy.
No, just joking. Go ahead.
Okay, so yeah. So here is the main part where you can see how regularized KNN differentiate from weighted KNN, because here you can see the line of the accuracy and macro F1 decrease straightly as K increase, decrease linearly as K increase. So so this is because the higher K values amplify the effect of majority class, and regularization keeps minor class recall relatively stable. And you can, if you remember, the weighted class versions is more unstable as K increase. That's because but the performance is actually better. So this is why I say our regularized KNN is a degenerate version of weighted KNN. Yes. So this is more. So our regularized KNN is more stable, but the good part is more stable. But the bad part is that it may not be as good as weighted KNN under some conditions. Yeah. Okay. Next slide. So this is just about the same as weighted KNN. Yeah. So the dominant classes has high diagonal dominance, and the minor classes has very low dominance. Yeah. Okay. Next slide. Yeah. So this part is also about the same as weighted KN, but the performance is slightly worse than weighted KN. If I remember, it's 0.985 on weighted KN, and here it's 0.965. Okay.
Okay. It's dropped.
What? Sorry. Can you repeat?
It's a drop of 2%.
Okay. Yes. So next slide.
Well, the fact that your elbow plot has no elbow, it's I have to think about it. Yeah. And K equals to 1 is the best model. Yeah, because here you use K equal to 1, right? Correct?
This one.
What is K here? It should
Let
be
me
1.
try and check. I use 2.
2?
Yeah. Yes, I use 2.
Interesting.
Okay.
Okay. Go ahead.
Yeah. So learning curve part is where you can see the main difference between weighted KNN and regularized KNN. So typically weighted KNN can achieve higher accuracy and macro F1, but it's unstable under some conditions, like different chaining fractions. And in contrast, the regularized KNN, since so you can see macro F1 and
You're breaking up a second. Let's wait a second. You're breaking up. Let's see. Hello. Yeah. Okay. Try to repeat the last sentence.
the regularized, since the mechanism of decision is so the result is stable. As you can see, the accuracy and they all as the training data, unlike the weighted. Yeah. Okay.
I see.
So next slide. Okay, so my part.
Okay, so so now let's move on to our results and conclusions. So our data set is it is important to note that this data set is highly imbalanced. So the NBA actually dominate the data, while other classes like near Earth or outer system asteroids have far fewer samples. So for our model, we focused on 3 key orbital features: the semi-major axis, eccentricity, and inclination. We then evaluated the weighted K and N algorithm with different values of K from 1 to 5. As you can see, K at K equals to 1, accuracy was 0.9462 with an F1 score of 0.9431, while at K equals to 2, the accuracy slightly improved to 0.9474, which was our best result overall. At K equals to 3, performance remains stable at 0.9473 accuracy and 0.94 F1. Beyond that, the model stayed consistent but showed a small trade-off in discriminability. Yeah. So our feature weights converged uniformly, about 1/3 for each feature, which means that the data normalization dominated the distance calculations and no single feature outweighed the others. So when we looked at class performance, we see that major classes like MBA, IMB, and OMB were classified with high accuracy, while minor classes such as AMO, ATE, and IEO had poor recall below 0.2. Then the 3D visualizations confirm these results. Near-Earth groups had overlapping boundaries, while outer system classes like TJN and TNO were much more sparse in distribution. Overall, our weighted KNN achieved high accuracy, around 95%, with the best balance at K between 2 and 3. So for future improvements, we could implement a class regularized KNN or synthetic oversampling techniques to address class imbalance, and also explore additional orbital parameters to improve separation among overlapping asteroid groups. So these steps, we believe, would help us move towards a more balanced and discriminative classification of asteroids across all categories. Thank you.
Yeah. I think we discussed these points, right? So, features, you could improve more features. You could have other weighting, and then the issue with the weighting of the features, right? That might depend on the fact that actually the classifier was flat horizon close to the initialization point. Okay, very good. Any questions? Any comments from you guys? You guys work well together. I think everybody was active, right? And everybody was speaking. Yeah. Any comments there? Okay, no comments. Okay, let's go to group E.
Hello.
Let's see. You realize now that, do you know that this time was the time to present, or did you have to check
no.
Slack? Or,
No, I don't.
Oh, you remember. Very good.
But we are in the little problem that 2 of our members are sick, so they can't present they're sick. And another person had personal matters to attend to. That was what we got explained. So we're 2 people who have a slide. So if you want us to not go through it all and they can go through it next week, then we can do that, or we can go through what we have right now and talk about what we found.
Let's do 50-50 right now. Let's do 50-50. Give me what you have today, and then next time we'll
okay. Let me find the must be this, and then oops. And all right, this is less than half of a group error for false work on on the KNN of asteroid data. So first of all, we have this asteroid data set from Kaggle. It has 45 features in total. Most of those will not be used, as that is maybe a little bit too much for our small brains to comprehend. Then we're going to take and split the data set into 80% training and 20% testing. This is usually done using the scikit-learn package to do this. Then we have the objective as that we want to do a classic KNN, then a weighted KNN, and then a regularized KNN and compare them. In this slide, there's not going to be any comparison because most of the people who did weighted and regularized KNN are not here. Next week. Okay. Well, I was responsible for doing the classic KNN algorithm, so luckily I can talk about that. In the classical one, we calculate the L2 distance between where we take the test data and take the distance, find the k nearest neighbors. First, we did this by just for loop. Then after that, implementing NumPy vectorization. And then at last, using a lot of Copilot, using a KD3 implementation that makes it
nice.
faster.
Nice.
And of course, here what we want to do is find which value of k, so how many neighbors should we look at, by just doing this for different k values and finding the one that is best in different performance metrics. We had a typebreak function also that we decided to go, or more so I decided to go for that the classes that appears most frequently would be the tie breaking, but you can easily argue that this should be the reverse, as if a lot of nearest neighbors are rare asteroids, then it's probably more likely that it should be those asteroids. Okay. First of all, if you look at the distribution of classes, we have that it is very not well distributed, as most of the classes asteroids are of class MBA, which means that if we want to evaluate on the accuracy of this of our model, it should at least have an accuracy higher than 89, because if we're below 89, then it would be better to just guess that it's an MBA asteroid and be done with it. Now we can also use other metrics like precision or recall to find out more about the less frequent classes if we predict those more correctly, and we should also try to optimize for that, while accuracy is more weighted against the more higher frequent classes. So we do this for k from 1 to 10, and find that k equals 4 is the one that has the highest accuracy, while if we plot the F1 score, which is a compromise between which is a value that is a compromise between how many, how often when we predict this class is it correct, and of this class how what percentage is correct. So we see that if we plot the F1 score for each of them, we find that the K2, k equals 2, has the highest value, the highest average value of F1, which is highlighted in this macro average. Plotting this as a confusion matrix, we find that while the frequent classes are pretty well classified, a lot of the classes that are less frequent, are more rare, are more likely guesses at some points where there's even one class that we don't get it correct at all. This is just for the two.
Can you go back one slide a second? I'm transfixed on this.
The other plot.
Performance. Let me try to understand it a second. Don't tell me too much. So why is this not monotonic? Why is this monotonic? Because of course you start what you're saying, right?
The way that it works.
Let me think a second. Let me think a second. If
it's
you tell
based
me
on the classes, maybe it's just the axis that's not named properly.
Let me think a second.
Okay.
So on the x-axis, you have the percentage of the data set, right? So of course, as the data set goes complete, right? Of course, this is pure.
No, it's not the sum. This is it's probably just a little bit confusing then. This kind of looks like the distribution. So the last point is the I'm pointing with my finger, not my mouse. The the last point is this MBA class. So it's the class frequency. That's should be clarified. So this point here is the F1 score for the MBA class. It's a little bit below 10 to the power of 2 in log. So F1 score of each class.
Percentage of the whole data set, right? So you take a certain percentage of the whole data set, and then you have lines for different Ks, and this is the average F1 score, correct?
Yes. Yes.
So you're telling me?
Oh wait, no, it's not the average. Sorry. That's the thing. These are these values. I don't know if you can see my mouse, but the F1 score is here, and then it's just mapped according to frequency in the data set.
Okay, so then you multiply by the frequency, and then you don't sum them.
Yeah, I don't sum them. Yeah, exactly.
Okay, so let's stay here a second. So can you tell me, just a second, why for k equal to 7, at 0% of the data set, your F1 score goes to 1?
I have no idea why. Also, it might not be because of the way that it's plotted. There might be overlapping lines because it's so not binary, but there's the least frequent one. There's 4 of them, and there are some of the predictor models which predict them correctly, and there are some that don't.
Understood.
So it's not necessarily only k equals to 7.
I see. Understood. And then why is this not monotonic, right? As you take more and more data sets, why isn't this curve monotonically increasing, right? Why for some percentage of the data set?
Well, you would expect that for it to, like in the you can see that for it's only at the low frequent values where you see larger variance in the different Ks, which makes sense as if we have a data set filled with the value of MBA, the K nearest neighbor on average is probably gonna be MBA, which of course will then lean the data set over towards that, and sort of as K increases, the more neighbors you take, the higher this effect is going to be. You're just going to find more MBAs in it. So if you have a high K, it should not be very good performing at the lower ends, while the lower Ks, which we see here is K2 and K4, perform better. And also the green one, which is K3 up here, because there's most likelihood that they might include 2 or 1 of the correct class that are then not being shadowed by the MBAs that just randomly happen to go in there.
Good. I don't understand it. I'm happy. Okay, go ahead.
Yeah. Okay. So this is the confusion matrix of both of them, of these 2 K values. And it's not really that good. Again, you see that it performs well on some of them. Most of them are the highly frequent ones, and some it just completely guesses wrong on, like the IEOs. So yeah, there's definitely work to be done, which hopefully is done with the weighted and the regularized. But here we also, then I just go and also have plotted the IRC curves. And again, it's very, like if you take the micro average, it looks very good. But again, the micro average is gonna be around just predicting the MBAs correctly, which should not be hard, as the MBAs are the just dominating class. But when you look at the different classes, there are a lot of them that are just not very good as well. Yeah. Oh, what? Did I move? Let me see. Okay, I moved them wrong. Sorry. I would stop there, but of course I have been listening for maybe an hour, maybe 1.5 hours to other people, and I thought, what are actually these asteroid classes, and which parameters should I include in my dataset? So I looked up the asteroid classes, and I do have a background in astrophysics, so I thought maybe I could bring some extra insight into this. Usually in astrophysics and astronomy, there are a lot of different systems that you use, and they are used by different people for different stuff. Here we have a data set that's filled with a lot of parameters, including a lot about orbits and a lot about the the brightness and how, if you take a telescope, how it looks when you look at it. So diameter and albedo. The classes that we use are all based on the orbits of it. You can find them here, where we have the main belt asteroids with orbital elements. So it's mainly about distance to the sun, where they orbit inside, which is also why you have the main belt asteroids are funnily the ones that are the most of. That's why it's the main belt. That would make sense. It's mostly about where they are positioned in our solar system, but there's also other classes that like the near Earth asteroids and very parabolic asteroids, so very high eccentricity, meaning that it's a very, very broad, very broad ellipse that is its orbit. Meanwhile, there's also another way that these asteroids can be classed, that is by taking the spectra when you look at them, which would give you the absolute magnitude, which is independent of the distance to the asteroid. It is how bright it is if you were 10 astronomical units away or something like that. I can't remember the precise definition, but it is independent of distance, this parameter. So even if a asteroid is far away, this should not be able to predict whether or not this asteroid is in these orbit classes. However, of course, if it is further away, then it should have a lower magnitude because it is further away from the sun, which is where it gets all its brightness. So maybe it actually does. The diameter is tells you something about the magnitude, because if a object will be larger, then it will usually also shine more brightly. And the albedo also, how much light is reflected. So how reflective a celestial body can tell you of what the asteroid is made of. And of course, when you have planet and asteroid creation, you tend to find that the more metallic asteroids will be further away. So they do have some cross correlation to these orbital classes, but they should not be used maybe as a way to define the orbital classes, but instead find parallels between them. So while there were PowerPoint going on, I tried changing the variables to the eccentricity, some of these values here. Values here, and for k equals 4, I find that it is way worse than what it was before. And now I'm just going to quickly stop, go into the Colab here, because I was running some code in the meantime from 5 to 10 to see if there's anything that's actually become better by doing this, because I was running this in the meanwhile. And it does not seem that the accuracy or the macro average improved here. So I'm hearing an echo. Okay, well, going back to the slides and going back to here. These were the original ones where we used. I should show. These are the original parameters that we use: the absolute magnitude, the diameter, the albedo, and then a lot of orbital parameters, but not all of them. And we found that we got an accuracy of 0.97 and a macro average of the F1 score of 0.7 for a best case scenario. And if we changed it to using these orbital parameters, we got way worse results, and it was worse at actually predicting it using the classical KNN. Yes. Now my other group mate will talk about the weighted KNNs.
Thank you.
Can you hear me?
Yeah.
Oh, okay. So basically, because the members are not just they finish the code, but they're not just how to explain this, so I have to look at the code and extract some important points myself. And I made this PPT, so maybe it is not that dedicated or correct. So I'm just going to go through them. So okay, next one we have the weighted KNN. So it is an improved KN method. So these methods assign different weights to each feature. So the important features will have more weights, and so this will make the important features contribute to the distance more. So here's how we are going to do this. So first, we make the weight all equals to 1 initially, if not given previously. And we calculate the distance by the formula shown in the slides. And we find k nearest points, and we determine the weight by the opposite of the distance. And then we return a feature with highest weights. So for simplicity, we tested weighted KN using two features like age and diameter, and we split the data set into training and testing sets. Okay, next page. Okay, so that we then optimize the feature weights automatically. We use the method to minimize the 1 minus accuracy as a loss function and minimize it with the Howell method. In the initial weights were 1 and 1, and we set the bounds to 0.1 to 5 for just to make it just not for some extreme values. So okay, then we finally minimize the 1 minus accuracy like I said before, and then we obtain the optimal weights and the corresponding accuracy like shown in the slide. Here, notice we use the minimize from
Scalar,
SDIPY optimized to find the optimal weight between 0.1 and 2. Next page. So yes, so we use this function to. 等一下，我在报告课呀。我在报告。And we use this to minimize, and so from 0.1 to 2, and the results are as shown. Okay.
Exactly. Again, you hit against your optimization boundaries, right? You get 5 and 5, right? So your optimization failed, right? Correct? Like go up one. And you see that you get you optimize between 0 and 5 and 0 and 5, and your optimal values are 5 and 5, right? So your optimization failed, correct?
Yeah, the limitation should be higher. Right? Again, I have not written this code and hasn't really talked about this, but I assume if the optimal weights go all the way up to the maximum, they're probably trying to go somewhere else, and we should then have changed the limitation so that it could go maybe higher or to other values, because clearly the weights that we're using are maybe not the ones that have the actual value optimized, but instead are just limited by the limitation factor.
Correct.
Yeah.
So next page. Okay. So to ensure stability, we repeated the test 50 times and averaged the results. And we computed accuracy, precision, recall, and F1 score, and compared the results for different K values. And so this allowed us to observe model consistency and find the best parameters. So I looked through the code, and we did the K values like 1, 3, 5, 7, 9, but the chart, the results, I don't see really much difference, so I just put one to represent the result here. Okay, next page. Okay, so here we have the regularized KNN. So first we do this, we generate data with 1,000 samples, 20 features, and 2 classes to test the model performance. And then we split it into 7% training set and 30% validation set. So first, we have 2 different ways to calculate the distances. So the normal one with just not weighted is the normal distance is shown as in the slides. So we can also choose whether we should enable weighted voting and return predicted probability. So the predict probability here is for the later balance coding part, and I'll cover it later.
Nice.
Okay, next page. Okay, here the next we have the class weight learner. The weight learner is what we use to find the optimal weight for each feature. So the step to do this is we first randomly generate weight combinations using Dirichlet random distribution, and then we train KN for each weight combination that we generated. And then we calculate accuracy on the validation set and find the best weight combinations. Okay, next page. Regularized KN is designed to address problems of class imbalance. So we need the balance decoding part to accomplish this. So these methods use class proportions from the training data and forces the final predicted labels to follow the same class distribution. So specifically, it converts the probability of each sample belonging to each class into a cost, and assigns samples to classes in order to the lowest cost and until the desired number of samples per class is reached. So this approach effectively prevents the model from being biased toward majority classes and results in a more balanced and fair predictions. Okay, next page. So in the final part, we also use grid search CV to tune hyperparameters such as the numbers of the weights and the distance metrics such as L2 and weighted L2 and both weighting. So, and then we assess the accuracy and macro F1 score, and the result is as shown in the slides. So yeah, this is what I concluded from the course. So
K equal 10,
maybe
K equal to 10, really. K equal to 10. K equal to 10 is your best K, right?
This is what my teammates did. So and
I'm very suspicious, right? Very suspicious. Very suspicious. And next week they're gonna tell us K equal to 10. It's out there, right? K equal to 10 is out there.
Yeah. So this okay. So we're finished. This is what I concluded. Okay.
Okay. Okay, very good. Yeah, let's try to to see next week what happens. Try to finish the report by Friday, and then next time you present and you tell us a little bit, because something a little bit fishy going on there.
Okay.
Yeah, but good that you have an interpretation of the features, right? Try to use the specific domain knowledge that you guys have in the team to do better. Okay. Okay, very good. The usual little break, guys. Let's take a 4 minutes break. I'll see you back at 3:30. Okay. Okay, guys, last push. Last few groups. Okay, so group E. So group E. Let me just check a second. Group D. So this is group E, half group missing, half group missing. We'll present next week. Okay, let's go to, we still have group F and group G, group F, last one. Okay, so I guess my brain is kind of tired as your brain is, I guess. So group F, come talk to us. Group F, where are you, group F? Group F. Stand by. Works in the aeronautical industry. Stand by.
Sorry, just give us a moment.
Very good.
Yeah, we're trying to share the slides and contact everybody.
It's been a long class, guys. A long class. Very good. Okay, group F. I see a softmax. Okay. And they also use CAD. Okay, very good.
All right, can you all see the slides?
Yeah.
All right. So let's carry on first. So we'll be doing just like everybody else, the KNN. So for my part, I'm Joel. Also Chen Xingwei and I will be doing classic KNN. So basically, some of the goals that I have for this is basically to optimize as much as possible the classic KNN and to keep it within 12 GB of RAM for the collab free collaboration, so that the free runtime, so that we don't run out of data. So
money, right? Of money, one of the two.
Of memory. So firstly, we need to do some data cleaning first. So we have dropped some of the data that we deem not required, and also remove some of the data that have missing data inside. And this is ultimately our values. We use HEAIQ. Like basically those columns are the data that we'll be running on plus the class. Okay, so carrying on. Firstly, I tried to do the knife implementation, which basically just using for loop to calculate the distance. Is pretty slow, and because it uses Python for loop, it's not really optimized. So this is probably going to take like 100 hours, 100 plus hours, maybe 200 hours to just try to calculate because of how big the data set is. So next, we try to do vectorization to make it faster. So what we do is we use NumPy optimized C code to basically run faster. We did some dot matrix multiplication as well. Basically, all of this is what it does is that instead of doing the multiplication one by one through a for loop, we use NumPy to basically do multiplication all at once. Basically affect all the data at once, calculate all the data at once, so that it reduces the time needed. And because NumPy uses C code, is inherently faster than using Python through interpretation. Yep. So however, vectorized implementation does have one big problem, and is that if you put everything inside, the NumPy array will be pretty big. So you can see in this case, we have 186K test data. if you were to calculate all the data with all the train data to calculate all the distances with 8 bytes of float64, we'll take 1 terabyte of RAM. And I don't know where I can get such amount of RAM, maybe from TSMC instead. Yep. So I was shocked when I saw this memory error. And so that means there's further optimization to do. So this is probably how it will be like. Where it says, yeah.
I appreciate memes. Let's just say I'm old, but I appreciate memes. Very good, very good. Go ahead.
Yeah. Okay, so how do we solve this? So we need to basically reduce the memory space. So the first thing that I did was to change from float64 to float32, which basically reduces all the space by half, and it's quite big. But because the values are so small, there's very little accuracy loss, so we don't really have to worry about that. Yep. And then the other part is that we basically do pre-allocation of memory so that it doesn't so that the Python interpreter doesn't need to keep allocating memory nonstop, and it's basically just an efficiency step. Next is that even if we do 50% memory saving, 50% of 1 terabyte is still 500 gig, which is a lot of data. So what we do is that we process the data in batches, and we basically do processing in batches so that we try to keep it under the 12 gig limit so that we don't crash the collab runtime. And lastly, another optimization that we did is we use up partition to find the smallest k value without sorting for the full array. So basically what up partition does is that instead of sorting everything from smallest to biggest, what it does is it just identifies the smallest part without fully sorting the array, making it much faster in runtime.
No, come again. Can you explain this again to me? Explain this again.
So for up partition, what it does is that instead of sorting the full array, so let's say you have 10 array of 10 numbers, and you need to sort them, and you want to find the smallest number.
Yeah.
The traditional method will be you sort everything first, and then you take like the smallest number, which will be the first value. But in this case, what up partition does is that it will not sort fully. It will just sort one part of the array, and will just give you the smallest number, which is what you need for the smallest k neighbor.
Okay.
Yeah. So this is the code as shown. Okay, so now we'll be going through the classic KNN results. We did 3 tests with 3, 5, and 7 across the full data set, which is actually quite huge, so it took some time. Without the optimization that we have done, you can see that it's 2,000 seconds. It's like, I think it took me 2.5 hours to complete just 3. So if we had the unoptimized version, which is like 100 times slower, it would be like 300 hours. Probably not enough time to do it. Yep. So some of the data, so overall, you can see that 3, 5, and 7, they are relative for k equal to 3, 5, and 7. They are relatively similar, but you can see that there's a very big problem with this. Is that if you look at the data for basically MBA is extremely accurate across all three for all three scoring, which is precision, recall, and F1. However, if you look at the rest of the data, they are like 0.5, 0.4, some of them are 0, some of them are 0.3, which means that the classic KN doesn't really work well for the rest of the data. And even though the weighted average for F1 score is 0.94 to 0.95 across all three K values, it's not a very accurate indicator because it's just basically predicting for MBA. Yeah, and it doesn't really predict the rest of the classes, which you can see through the confusion matrix as well as the full classification report as shown below. So these are some of the results, and as mentioned earlier, even though it may look pretty accurate, in reality it only predicts MBA. So that is what something that can be worked on, which will be through weighted KNN, which my groupmate will go through after this. Yeah.
Hello. And this is my part, weighted KNN. So weighted KNN is unlike the classic KNN. It has the weight, parameter, inside, and the classic KNN is always take the weight like to be 1, so everyone is the same. And weighted KNN tries to make the some data may have the more weights to calculate the result. Yes. So and so we have this method. And next page. We try to calculate a weight by this function, and we basically mainly use this minimize sci-fi minimize function to get the best weight. And in this function, we use the right code here, and we try to use this weight KN model, weight KN classifier. And yes, so next page. We try to calculate the L2 distance method.
And distance plus epsilon. Yeah.
Yes, and add with weights, and we
Google suggestion as well.
Yes. So and I am still working on it. So next page.
Yeah.
The result is still running. I just still working on it, so I can get the analyze something. Yes. So maybe I will try my best to do later. Okay.
Yeah, just be careful. Like you saw also the other teams that this optimization. If you just use fmin, right? So it's you have to be careful of whether the results of the optimization make sense. Okay. Go ahead.
Okay. That's it. And this is also the result I am running. Okay, that's it.
This is my part of the challenge 1, and my job is to optimize the weight. So the way I choose to optimize the weight is the SLSQP because it supports the boundaries and some constraints. So I think this is a good way to optimize it. And then I throw the way that is optimized into the sklearn classifier. And next page. And this is the code about the SLSQP and throw in the sklearn library. And next page. This is the result of the KNN classifier, but I think the runtime and it's really weird compared to the last one. So I think there is something wrong. So maybe I need more time to check the code, but the accuracy is quite high. Okay, next page. And this is a different case about the algorithm. And like compared to the classic KNN and the weighted KNN, for the 3k equals 3, the weight can have do much better than the classic one. But if the k goes higher, the accuracy may be lower because the the overfitting and the cape will make the data more average. Okay. And about the metrics, I still meet some problem. So maybe you can see at Friday. Okay, that's my part.
Very good, very good. So, but when you do these experiments, you still use the full data set optimized in batches as in the first part, right? So you use all the features. So you have a weight for all the features, correct? Is that correct?
Could you repeat again?
So in the first part, right, we discussed the using batches for like how to optimize the use of all the data set for KNN, and the
Yeah.
inference time is still very large. So in these
Yeah.
experiments that you do you still use the technique? You still use the model of the first part of the discussion?
No, I use the sklearn one, not the model do by the group member.
Okay. Okay. Yeah, because the inference time is so quick. Yeah.
Yeah.
Okay, go ahead.
Okay. My part is over. Okay.
Okay, and my part is vanilla KNN because our data set is highly imbalanced. So vanilla KNN ends up predicting the dominant class most of the time. That makes raw accuracy look okay, but macro F1 and balanced accuracy collapse. Our goal is to raise minority class recall without blowing up rare classes. So the overall macro F1 and balance accuracy improve in a stable, trustworthy way. Next page. We combine three simple pieces. First, prior weighted voting alpha. Class weight scale inversely with the training prior P of C with clipping and a bit of uniform blending to prevent rare class explosions. Second, distance decay. Beta. Neighbor weights follow 1 divide D plus, sorry, I can read that symbol.
Epsilon.
Thank you. And beta times. So larger beta gives closer neighbors more influence. Third, IPF collaboration. We adjust predicted probabilities so the average marginal matches the training prior. Next
So what
page.
is IPF here in frequency? What IPF? What does
IPF?
IPF stand for?
Right. I don't know. I searched it from internet.
Let me go. Let's Google it. Let's see who is faster. IPF calibration.
Iterative proportional fitting.
Thank you. Did you look it up or do you remember it?
No, I look it up.
It's your presentation. You should know what goes on your slide. Go ahead.
Okay, so next page. So the flow is find the k nearest neighbors, then apply alpha prior weights by class, and apply beta distance weights by neighbor, and aggregate with softmax into probabilities, run IPF calibration. This balances local evidence against the global prior, so we don't swing between all majority and the overboosted minority. Next page. Before collaboration, the predicted class marginals scoop, either collapsing into the majority or over-amplifying minorities. After IPF, the average output distribution aligns with the training prior. This avoids both extremes and it makes the scores credible. From there, we judge improvements using macro F1 and balanced accuracy, not just raw accuracy. Next page. And we're comparing vanilla KNN with our best regularized setup. Minority classes light up while the majority remains stable. In other words, we are not injecting chaos. We are distributing performance more evenly across classes. You will see clear gains in macro F1 and balanced accuracy under the best K, alpha, and beta. Next page. With K is 11, a larger beta strengthens locality, so truly close neighbors carry more weight. Alpha, when alpha is 0.5, is usually steadier than alpha is 1.0, which can overcorrect ultra-rare classes. Net effect, minority recall rises without letting a single rare class dominate. Next page.
Can you tell me what is your beta for this K equal to 11? What is the range of beta?
My beta is 2.0 and 3.0.
Wow, so you use a large neighborhood, right? But then the decay factor is so aggressive.
Yeah.
Interesting. Interesting. Go ahead.
Next page. So when K is 21, voting is naturally smoother. We still tune minority recall with alpha and beta. The trade-off is classic. A larger K suppresses noise, but if beta is too small, locality weakens and minority signals get washed out. Our settings show how to avoid over-smoothing while keeping stability. Next page. This is a picture. And next page.
So wait, what was the beta there? What was the beta? Beta is still 3 and 2. Okay.
Yeah, still 3 and 2.
Did you force the beta to be integers? No, right? Did you force the beta to be integers?
Yeah.
Okay. Okay. 31. Go ahead. Tell me about 31.
And when K is 31, variance drops and stability peaks, but over-smoothing risk is highest. Beta is the locality level. Beta is 3.0, lights up more minority cells. Beta is 2.0, leaves majority dominance stronger. Alpha is the prior level. Alpha is 0.5, is safer. And alpha is 1.0, can overcorrect on ultra-rare classes in some folds. We always select by macro F1, then balance ACC, then accuracy in that order. Next page. And this is a picture. Okay, and next page. So the three takeaways. First, plan KNN fails under imbalance. Second, alpha plus beta plus IPF is a cheap, interpretable fix that lifts macro F1 and balance accuracy without wrecking stability. Third, simple preprocessing, balance training plus PCA usually aids a bit more reliably, and for model choice, we prioritize macro F1, then balance accuracy. And
Wait.
accuracy.
Why did you put PCA now? Where was PCA? You didn't say any PCA, right? Where was PCA?
Yeah.
Where was PCA?
Principal component analyzer.
Oh, where? Actually, we're here. I'll slap you. I'm joking. Where did you use it in this present? I'm joking. Okay, I'm joking. Where did you use it in this presentation?
What?
Did you do PCA here?
No, I just put some for example, for summary.
Oh, okay. Because because now you mentioned PCA, but you didn't do any numerical experiment with PCA.
Yeah. I just search information, and I think is relative to that thing. Yeah.
Okay.
Good. And that's all.
Okay. Very good. Thank you, guys. Thanks. Okay. Very good. Yeah, there are a couple of things missing, so I hope to see them in the final presentation in the final report that you present on Friday. Okay. Okay. Very good, guys. So just a little bit of recap. Friday we release the new challenge, the new groups. I'm pushing for the evaluation form. I'm running a little bit behind. I have to push the TAs a little bit. We have 2 late presentations, right, for next week, which is okay. And then, yeah, that's it. So submit everything by Friday, and then the presentation, we can do it next week. Anything else, guys, that you want to discuss? Otherwise, I'll stop recording, mute my microphone, and I'll see if there is anything else. Any other comment, guys? Okay, very good. So I want to go running with you guys, but the temperature is still crazy. We cannot go running at 5. So let's wait till the temperature goes down, and then we go run together. Okay, very good, guys. I'm gonna stop recording, and then you can ask me questions, and then we start the class. Okay, ciao, guys.